of our morning session, which is by Golowich, and he'll be speaking on approaching the quantum singleton bound with approximate error correction.
Thank you. Yeah, so this is joint work with Thiago and Sam. And I guess I'll start by just giving a brief recap of error correction in the classical or the quantum setting. So we just have some sort of message, which I'll call phi throughout this talk. And we assume it's length k, so it is k symbols. And the typical setup is that we'll run this message phi through an encoding algorithm, which gives a length n code word here. And then we assume that this code word undergoes some errors. So some adversary A can act arbitrarily on this code word. But we need some assumption on A, so we'll assume that it is a weight at most delta n, which means that it corrupts at most delta fraction of the code word symbols. And then we assume that our code comes with a decoding algorithm, which we can run, and it outputs a message phi prime, which hopefully is equal to the original message phi. So formally what we want is for a given rate, r equal to k over n, which is the rate of redundancy in our encoding. We want efficient encoding and decoding algorithms such that the output phi prime of the decoding algorithm is equal to phi for the maximum possible fraction delta of errors on which the adversary acts. So this is like a really fundamental problem. It's kind of the fundamental problem in error correction. And there's also fundamental upper bounds on how well we can do. So if we know the locations of the errors, then the singleton bound, the quantum case, the quantum singleton bound says that for a rate k over n, so if the redundancy of our encoding is rate r, then we can only correct from errors on at most 1 minus r over 2 fraction of the code word symbols. Whereas if the errors occur at unknown locations, so we don't know where the errors happen, then this drops by a factor of 2. So we can only recover from errors acting on 1 minus r over 4 fraction of the symbols. Now this first bound turns out to be very robust. The intuition is that it's kind of based on no cloning. So if r is very small, close to 0, then this says that delta is at most 1/2. And indeed, you can pretty intuitively argue that we should never be able to error correct from errors on more than half the symbols, because in that case, we could kind of take our length n code word, split it into 2 halves of length n over 2. And each of these halves, we've lost half the code symbols. So if we had a decoding algorithm, we could apply it to each of the 2 halves and recover 2 copies of the original state, which should be impossible. So this 1 minus r over 2 bound is very robust, whereas this 1 minus r over 4, there's kind of no similar reason to think that it should be really robust. So the question we'll ask in this talk is, can we close the gap? Can we find some relaxation of error correction where we can actually, for errors at unknown locations, recover from 1 minus r over 2 fraction of the errors? And the approach we'll take here is to relax to approximate error correction. So before with exact error correction, we actually want to precisely recover the unique state. But for all practical purposes, if you recover a state that's maybe exponentially close to the original state, so maybe differs from the original state by like an inverse exponentially small loss in fidelity, then basically for all practical purposes, you're still doing error correction. But interestingly, it turns out that if we relax to just requiring this approximate error correction, so we're okay with this very small loss in fidelity, then the 4 that we had known here actually changes to a 2. So now there's no fundamental reason that we can't correct errors. We can't correct from up to 1 minus r over 2 fraction of errors.
Is there any situation now where you will do separate these ones for the known error location?
Where you, as in codes that achieve this bound? Yeah. So actually, the main result of this talk is that we'll achieve this bound.
Oh, yeah. You will construct codes.
Yeah, exactly. So yeah, we want to construct codes that literally reach this bound.
But this was already known for the case of known error locations.
Yes. So yes, the answer is basically yes. If you want a constant size alphabet, I'm not sure it was explicitly observed, but it's not too hard to get.
The polynomial code Approximate codes with what?
With like, yeah, AEL. Concatenation will hurt your distance, but I'll actually talk about later. We can do some distance amplification. So yeah, even that I think wasn't explicitly observed before.
Just checking my understanding. So the important point here is efficient construction, right? Is otherwise random.
Yeah, perfect. Yeah, that's a good point. Random codes actually achieve all of this. So it's really efficiency.
And the approximation is exponential, or yeah, how good is the approximation that you want?
Yeah, inverse. So the fidelity difference will be like, or trace distance will be like 1/2 to the order n. So our main result is just this. It's for every possible rate and for every gamma, which you can think of as like some small constant, then there exists a family of approximate quantum codes with rate r, constant alphabet size, assuming gamma is a constant, that correct arbitrary adversarial errors on 1 minus r minus gamma over 2 fraction of the code word symbols up to an inverse exponential recovery error. And formally, just saying that if we have our message phi, we encode, the adversary acts on delta fraction of the symbols and we decode, then the distance, this could be trace distance, it could be fidelity loss, it could be actually like diamond distance of the associated channels, which is actually what we want. But in all these notions, we have inverse exponential loss.
I'm missing, so why don't random codes satisfy this theory?
Oh, sorry. Yeah, I should say efficient.
Yeah, so it's the correction is efficient.
Yeah, encoding and correction. Yeah, sorry, that's a really important point, actually. So interestingly, this actually has no classical analog. So the goal of classical error correction is the same as the goal of quantum error correction. And there's a classical singleton bound that's analogous to the quantum singleton bound, but it's double the quantum singleton bound. So for known error locations classically, we can only correct up to errors acting on 1 minus r fraction of the code symbols, whereas quantumly is 1 minus r over 2. And when we don't know the error locations, classically this drops by a factor of 2, as it did quantumly. And again, for known error locations, it's a very robust bound. It's actually even simpler than the quantum argument. It's basically just like a pigeonhole counting argument. So naturally, you could ask classically, can we do the same thing that I just said we can do quantumly, and can we kind of somehow relax the notion of error correction, to approximate error correction, and get back up to this 1 minus r bound for errors at unknown locations. And interestingly, it's actually just in general impossible to correct errors in unknown locations on more than half the symbols. This actually holds both quantumly and classically. The reasoning is simply that if your adversary could act on half the code word symbols, they could just take half of your code word and instead inject the encoding of some completely different message. And you'd have no way, when you receive this corrupted code word, you'd have no way to tell which half they acted on. So which of these two halves contains the encoding of the true message. So it's almost like this classical quantum separation is almost like we've shifted the goalposts, because quantumly, the singleton bound is lower. It's never above a half. So this kind of general argument, this impossibility result, doesn't really apply. Whereas classically, the singleton bound is so high that actually there's this fundamental limitation. But nevertheless, there does seem to be a quantum classical separation.
Can you explain the last few words? What was the last bit?
Oh, so I guess, sorry, I was just kind of repeating. Quantumly, we can close this gap between 1 minus like the singleton bound and half the singleton bound. Classically, we can't. Though in both the reason we can't do it quantumly, the reason we can't do it classically, the reasoning still works quantumly. It's just this 1/2 is like an absolute constant. Whereas the quantum singleton bound is already at most a half. So. Right, so I'll now start talking about how we actually prove this result. And to start, I'll just describe this classical notion of list decoding, which we'll see actually will help us kind of surpass this 1/2 barrier and approach the singleton bound. So classically, if we have some classical message fee, again of length k, then in list decoding, we want to encode it again to a length n code word, such that if an adversary acts on delta fraction of the symbols, then we can decode. But now instead of decoding to a single message, we run a list decoding algorithm, which outputs a list of like some short polynomial or constant size list of possible messages. And the guarantee that we want is that the true message fee is contained inside this list. So we just need one of these list elements to equal fee. And again, the goal down here is for a given rate, for a given redundancy rate in our encoding, we want efficient encoding and list decoding algorithms so that for all weight delta n adversaries, the message is guaranteed to be contained inside the output list.
Interrupting, but I just wanted to compare quantum and classical. If you take your result with the quantum approximate codes and you make it into a classical result by basically measuring and just looking at the single basis, how does this compare to the classical case?
Okay, so this will, I think it will still correct against 1 minus r over 2 fraction errors, whereas the classical singleton bound is 1 minus r. Mm-hmm. So you'll be off from the classical singleton bound by a factor of 2. Right, so we have this notion of list decoding. At least we have it classically, and it turns out that classically you can list decode from twice as many errors as you can unique decode from. So as I mentioned, classically the singleton bound says for ordinary unique decoding, you can't decode from errors acting on more than 1 minus r over 2 fraction of the code word symbols. But if we relax to list decoding, where we just need a list of messages, one of which is correct, then we can get back up to the true singleton bound of 1 minus r. And actually, there are efficient constructions known classically due to Guruswamy and Rudra that exactly achieve or that get very close to this bound. So this suggests a possible approach to approximate quantum error correction approaching the singleton bound. The idea is if we could first somehow develop some notion of quantum list decoding, which is correctable up to 1 minus r over 2 fraction errors, so up to this quantum singleton bound, then we've kind of gotten halfway there. We've gotten a notion of error correction at the singleton bound. And then we just need to kind of reduce approximate error correction to this list decoding that we assumed we could get. So I guess this is kind of like, it's almost like a wish list of like, this is maybe one approach we could take. And the motivation is just that classically list decoding seems to get us to the singleton bound. So maybe we could do the same thing quantumly. Now there's some issues that come up. The first is like, how could we possibly do quantum list decoding? The whole premise of list decoding seems to be that we output a list of messages which are all correlated with the true code word. And quantumly, this just seems impossible by no cloning. Like we want a list of quantum states that are all correlated with the true state. That sounds pretty hard. If it is possible, we still need to do this efficiently. And for this third step, we need some reduction from approximate error correction to list decoding. And we know that this is impossible classically, because I argued that classically, we actually can't close the gap between like the 1 minus r and 1 minus r over 2 gap, whereas we're trying to close this gap quantumly. So somewhere we're going to have to do something quantumly that doesn't work classically. So despite these challenges, this will actually be the approach we take. And it turns out that for all of these steps, there's been some prior work that helps to make progress towards answering these questions. Though in all three cases, we kind of will also need to do some additional work to get our result. So for this first problem, like how can we possibly do quantum list decoding without violating no cloning? Well, classically, we typically think of a list decoder as outputting a list of possible messages. But an equivalent formulation is to have the list decoder output a single message and then output like a concise list of possible errors that could have occurred on that message. And this latter approach actually is perfectly fine to do quantumly. This was originally proposed by Lung and Smith, and we kind of simplify their formulation and give an efficient construction in this work. But basically, the list decoder will output a quantum message, V prime, with a list of classically described errors. They'll actually be Pauli errors, E1 through EL. And this will be some like polynomial-sized list. And then the guarantee is that the true message can be obtained by applying the inverse of one of these errors to the state V prime that the list decoder outputted. So it turns out that this doesn't violate no cloning, and we'll be able to construct it. There are some subtleties in this definition that arise from code degeneracy. So I guess if you're aware of like stabilizer codes, it's actually the case that this list could be exponentially long if there's a lot of low-weight stabilizers. And when I say that EI is in L, I really mean that there's some logically equivalent error to EI inside the list, but that's just kind of a side remark. Oh, so we now know that we can at least define quantum list decoding, but we also want to do it efficiently. And classically, again, we'll go back to the classical case. So classically, there's these codes introduced by Guruswamy and Rudra called like folded Reed-Solomon codes, which approach the classical singleton bound with list decoding. And it also turns out there's this type of code called a CSS code. It's a quantum code that literally just takes two classical codes satisfying a certain orthogonality relation and combines them into a quantum code. And what we observe is that if these two classical codes are efficiently list decodable, then so is the quantum CSS code that they form. So this suggests a very clear approach, which we basically take, which is use these classical folded Reed-Solomon codes in a CSS construction. But as I'll describe later, we will need to do some additional work to make sure that we have a constant alphabet size. And I guess the third thing that we need to do is reduce approximate quantum error correction to list decoding. So once we have our list decodable code, what it'll do is after some corruption, it'll output like some quantum state and then a list of errors. And our goal is to identify the true error in the list so that we can invert it. And the observation here is that it's actually sufficient to pre-encode the message in some code that detects all the extraneous list elements. So we've kind of reduced our problem from detecting arbitrary bounded weight errors to just detecting and correcting from errors in this list that are not the true error. And this is a much easier task because now we only have polynomially many possible errors. So in particular, like a high rate random code will probably detect all of these polynomially many bad errors in the list.
But you don't know this list in advance, right?
You don't know the list in advance, exactly. So the key point here is, I guess the key word here is random. For any fixed list, if we first fix the list and then have a random code, then with high probability, we'll be able to correct all the bad list elements.
Just a question about the previous point. Is it approximate or exact, the list decoding?
The list decoding is exact. Okay. The approximate is in the reduction to approximate error correction. Right, so I guess for any fixed list, then a high rate random code will with high probability detect all the errors. And I guess the approach we take, which is motivated by this previous paper by Lung and Smith, and is subsequently simplified in a follow-up work by Thiago, one of our co-authors, was that it actually suffices to use so we don't need a fully random code here. We can actually just use a pseudo-random code, which is this thing called a purity testing code, or a PTC.
All right. I'm maybe confused, but why? So you're basically very sort of a high level. You can just correct if the list is small enough so that basically you can correct even the list. But why can't you do it classically? Or maybe you can?
Yeah, that's interesting. So you can actually do all of these steps classically, except for this last thing. So this last thing is we're going to take some high rate random code, which will kind of filter out our list and find the right error with high probability. But we still need to transmit to the decoder, like, what is this random code, so that they can decode it. And somehow so that's like a transmission of classical information. We'll have a classical ensemble of random codes. And somehow transmitting this classical information to a decoder. So the adversary, like, we somehow need to encode this classical information such that even if the adversary perturbs it, we can still recover it. This step somehow you can't do classically. I guess the intuition is quantum. Like, in the quantum case, we'll use a classical robust secret sharing scheme, but that can only recover up to errors on half the symbols.
Okay.
So yeah, I'll get into all this more later, but that's the high level.
Here, pseudorandom, like the pseudo part is cryptographic pseudorandom, or?
Yeah, so the techniques are kind of cryptographic, but it's all unconditional.
Okay.
So it ends up being like statistical. All right, so I guess just to recap, here's the 3 steps, which I'll now go into more detail for. So we kind of have our notion of quantum list decoding, which in a second I'll present the CSS formulation of this notion, which is the one we'll actually use. We then kind of introduce these efficiently list decodable quantum codes, which really just combine these classical techniques and translate them to a quantum setting. So we construct CSS codes from these folded Reed-Solomon codes. And then there's actually some subtleties. We need to do this alphabet reduction case kind of quantumly instead of classically, but we'll see how it all carries through. And then we finally construct approximate codes from list decodable codes. And there's actually kind of 2 approaches here. The first one I'll mention combines these known cryptographic primitives, the purity testing codes, which I mentioned, along with the classical robust secret sharing. In this follow-up work, Thiago developed a more powerful technique for filtering the list, which actually introduces a new quantum cryptographic primitive called the Pauli manipulation detection codes. And this has some advantages. It removes the need for robust secret sharing, so it also allows for working even over binary alphabets. So I'll now give the formulation of list decoding for the special case of CSS codes. So given classical codes CX and CZ satisfying certain properties, these properties are precisely just that CX and CZ are linear codes such that CX contains the dual of CZ. But if they satisfy these properties, we can construct a quantum code, CSS of CX-CZ. And to decode, to just perform ordinary unique decoding on these CSS codes, what we do is we perform a measurement that projects any low-weight error to a Pauli error. So whatever our arbitrary adversary was before, after this measurement, the error is guaranteed to be some x error, EX, times some z error, EZ. Then we can basically just run the decoder for x in the x basis to recover EX, do the same in the z basis to recover EZ, and then we've now determined what our error E is, and so we can invert it. So for list decoding, in this setup, it's basically the same operation. We just replace ordinary unique decoding with list decoding. So we again perform this measurement that projects to a Pauli error, but then we'll run the list decoder in each of the x and z bases to get lists of possible Pauli errors, or lists of possible errors, EX and EZ. And then the final list we output is the set of all products of an x error and a z error. So it's the set of all x to the EX and z to the EZ, for EX in our x list and EZ in our z list. And we say that list decoding succeeds if the true Pauli error E is contained inside this list we've output. And now we have our notion of list decodability for CSS codes. We say a code is delta L list decodable if for all errors of weight MOS delta n, this list decoding algorithm succeeds. So it outputs a list containing the true error and the list size is at most L. So now I'll show how we actually construct efficient quantum list decodable codes. As has come up before, random codes are generally pretty good. And indeed, in this case, random classical codes are list decodable, which implies that we can get CSS codes that are basically optimally list decodable. So we can get CSS codes with constant list size approaching the Singleton bound, but these are random, so there's no efficient list decoding algorithm. Now, classically, as I mentioned, this is solved by taking like folded Reed-Solomon codes. This theorem of Guruswamy and Rudra basically says that there's efficient classical codes of any possible rate that correct against 1 minus r minus gamma fraction errors, so almost at the classical Singleton bound with polynomial list size and polynomial time decoding algorithm with a constant size alphabet. And this construction simply consists of these folded Reed-Solomon codes, which are what we want, except they have a polynomial size alphabet. And then it combines it with this Alone-Edmonds-Luby expander-based alphabet reduction technique to bring the alphabet size down to a constant. So basically, we just kind of stick the word quantum in front of everything here, but it doesn't quite work perfectly. So the first step works. If we take 2 folded Reed-Solomon codes, then we'll get a CSS code that's list decodable up to almost the Singleton bound. But the problem is we have a large alphabet size. And it turns out we can then apply this expander-based alphabet reduction technique. We can't just take the alphabet-reduced quantum code or classical codes, though, and apply CSS directly. Instead, we have to kind of apply the alphabet reduction on the CSS code itself. So we need like inherently quantum alphabet reduction technique. And interestingly, like this AEL technique was used in a number of different papers, a number of works classically, whereas quantumly it doesn't seem to have been used before, and it kind of immediately gives us some new implications for quantum codes approaching the Singleton bound, which I'll get to in a second, but first I'll just actually describe the technique. And also describe like why it works quantumly basically as well as it works classically. So to do this distance or this alphabet reduction technique, which actually also serves to amplify the distance of codes, we start with some message and we encode it in a large outer code. So here we can think of this as being like some high rate folded Reed-Solomon code. And following this outer encoding, we're going to encode each symbol in some small inner code. So this will have maybe be logarithmic size, so we can choose like a random code and everything will still be efficient because it's so small. So we kind of concatenate this outer like folded Reed-Solomon code with a random inner code. And this gives us basically kind of a new large code word with a bunch of like small inner code blocks. So here I've had the inner code block be size 6, so you can see kind of every original symbol is mapped to like a block of 6 new symbols. So then what you do is you see we can actually do reblocking. So I've reblocked each of these 6 symbols into kind of 2 blocks of size 3. So our new alphabet is 3 of these kind of little symbols. And this would be good, but it turns out that this just concatenation alone of the outer and inner code won't have good distance. So to amplify the distance, we actually just permute these symbols according to an expander graph here. So basically, we like push the symbols through the expander graph. So just as an example, if we take these 3 symbols here inside this first block, you can see there's 3 outgoing edges. So we just take the first symbol and push it along this edge and map it to this symbol here. For the second symbol, we map it along the second edge, and we do the same for the third.
Sorry, what happens if when 2 symbols map the same one?
Right, so I guess maybe this drawing isn't clear, but each of these blocks down here has 3 incoming arrows. So we just have we just order them in some way. Like the 3 incoming arrows are going to be the 3 blocks, like the 3. Okay, so there's 3 incoming arrows, and each one is carrying a single symbol. So we have whatever the first, yeah, whatever the first incoming arrow is, that's the first symbol. Second incoming arrow is the second symbol, and so on. So it's, the second step is purely a permutation of symbols.
So this permutation is here is a pseudo permutation, or?
Yes. So yeah, this is the graph here is just needs to be a good spectral expander graph, which there are explicit constructions. So yes, no actual randomness is needed in any of these steps.
Do you want me to use adversarial noise?
Yep.
How does the permutation help?
Yeah, that's actually what I'm about to say. Perfect. So if we assume that we have some corruptions, so if we assume that this final code word is corrupted, since we've defined each of our new symbols to be a block of 3, that basically means that we have some red blocks here, which are the corrupted ones. And as you can see, when we unpermute, it kind of spreads the errors out throughout all of the code, the inner code blocks. So now our red errors are kind of distributed throughout in a pseudo-random way. And the point now is that these errors aren't too concentrated in any given spot. So when we apply these inner decodings to each of these blocks of 6 symbols, by the pseudo-random property of expander graphs, most of these blocks will only have kind of a small fraction of corruptions. For instance, in this drawing, if we assume this inner code can correct from 2 errors but not from 3, then this decoding will succeed whenever the block of 6 has at most 2 red symbols. And you can see there's only 2 blocks, kind of this one here and this last one here, that have more than 2 red symbols. So basically, we've succeeded in this inner decoding has successfully recovered the symbol here in all but 2 of the possible positions.
But how do you know the errors in the bottom layer level are not, they're chosen adversarially, like you just chose them so that when it permutes it makes things worse and you don't concentrate?
Right. You could try to do that. It turns out that property of expander graphs is that you actually can never do that.
But does this mean that the errors are, the expander graph is sort of a known fixed random permutation, but not known by the...
Yeah, so it's completely explicit. It's a little counterintuitive.
But I mean, clearly I can, because I could just take each one-to-one significant permutation, right? So I could take errors a small number of errors that were 3 in each block, and then just look at what that looks like when I expand it. I
see. Yeah, sorry. Maybe, so I guess the idea here is that we have some flexibility because we have blocks of symbols. So the point is the decoder is a little constrained. They're only allowed to corrupt an entire block, or like for every block, they either corrupt all 3 or none of them.
Why is that?
Or I mean, they could corrupt one, but if they corrupt one symbol inside this block, it counts as a corruption on the whole block because we've defined our alphabet to be sets of 3. So yeah, it's kind of a strange thing where like, it's almost like we're defining away the problem.
Yes.
We kind of have this alphabet, like we have a larger alphabet, which means that the errors have to be clustered.
Okay. So it's just defining this as this is one symbol from the alphabet now.
Yeah. So yeah, this technique is very reliant on having non-binary alphabets, which we'll actually come back to later. But yeah, I guess the point is, if we take this larger, this alphabet of 3, and then we do this out, you can see that kind of here we end up with only 2 errors on the outer code word, which maybe the decoder can decode from, whereas if we just tried to not do this permutation step, we actually would have had 4 different blocks of 6 with at least 3 errors. So if we hadn't done the permutation, there would be like 4 different red symbols up here, and that might be too much for the outer decoder. So I'll also point out that this entire argument is completely general. It works classically or quantumly. All we're really doing is like we concatenate these two codes, and then we like physically move around code word symbols. So there's no reason it doesn't work quantumly, even though it seems to have not previously been used quantumly. And as an application, we immediately get quantum LDPC codes approaching the singleton bound. So we take all these recent works, this recent very nice line of work that constructs asymptotically good quantum LDPC codes. So quantum LDPC codes just with some small constant distance and rate. And we apply this technique here, which both reduces alpha, but in particular amplifies the distance of codes. And it gives us, for any rate, quantum LDPC codes of rate are distance at the singleton bound, so 1 minus r minus gamma over 2. But of course, that means unique decodable from only 1 minus r minus gamma over 4 fraction errors. And some large constant alphabet size, and these even have linear time decoders. So that's kind of just a nice side benefit we get immediately from this AEL technique.
So maybe I missed it, but why were you not able to apply the alphabet reduction before applying the CSS construction? Codes?
Yeah, I think the real reason is we need this. I think it's a bit technical. Basically, we need the orthogonality conditions to be satisfied.
I see, and the alphabet reduction breaks the orthogonality.
Yeah, if you try to like naively do AEL, I think it'll break that. You can end up looking at it as a kind of like CSS code of classical codes, but you then need to kind of slightly redefine a classical code to like be like a coset code, basically because of like degeneracy issues.
So you can kind of go back from the AEL construction applied to the quantum CSS code and like kind of get back the two codes that you.
Yeah, exactly. Yeah, you can take it apart, but it looks a little funny. So I guess now I'll go to the third part, which is we have our list decodable codes, and we want to get approximate codes from them. So this is what I've hinted at before. Basically, the question is, how can we choose the correct list element from the list decoder output with high probability? And as I mentioned, the solution is basically to encode in this purity testing code. So this is like, we have some family of codes, PTC, indexed by a classical key kappa. And what we want to do is choose a random element of this family, PTC sub kappa, which has the property that it detects any fixed Pauli error E with high probability over the choice of secret key kappa. So we first fix the error E, then for a random kappa, a code in this family will probably detect that error E. So the point is now, if the list decoder outputs some state psi along with a list of possible Pauli errors, we're guaranteed that some of these errors, like one of these errors, E sub I, is the true error that occurred on our state, and we just want to identify it. Because if we can identify it, we can invert it and recover the true message. And by this PTC property, we can literally just loop through all the errors in the list and test if the PTC detects an error. So like kind of try inverting that error, test if the PTC detects an error. If it does detect an error, then we assume it's the true error. If it doesn't detect an error, we unapply that error and move on. And by a union bound over the list, because the list is small, like polynomial sized, with high probability, the PTC will detect all the extraneous errors. This might make you a little nervous because like if this detection step is like a quantum measurement, are we perturbing the state so that like maybe these different detection measurements don't commute? It turns out that we can basically do a single stabilizer measurement ahead of time, and then all of this stuff is classical. Like all of these steps are classical, so it's actually a non-issue. But you can also argue like through a general measurement argument that since each of these detections happens with such high probability, the perturbation to this state will be negligible. All right, so this is great. We can filter the list, but from filtering the list, we've kind of picked up this classical secret key that we need, kappa. And we really need to hide the secret key from the adversary, because if the adversary could access the key, they could tailor their corruption to whatever PTC we've chosen and kind of break the key property of the PTC. So the solution here is to actually encode the classical key kappa in a classical robust secret sharing scheme, which is just some keyless classical randomized encoding scheme that both hides the input from any bounded weight adversary. So it's hiding our secret key, and it allows us to recover the key even if the adversary tries to corrupt this encoding. And these robust secret sharing schemes classically are already known.
All right, I'm a little bit confused about this hiding notion. So you're thinking of quantum error correction as, so we can think of this in two settings. One is in order to correct errors, I don't know, in a physical device, and another in a more cryptographic setting. And if I'm just interested in the first setting, does this make things easier?
And like the non-cryptographic setting?
Yeah.
Yeah, so I guess then if you're, like maybe you're fine, in that case you might be fine with just holding a classical key. Like you could imagine if you have some like quantum computer, you draw a classical key, you implement your code, you can just tell the decoder, like you just store the classical key, so you don't need to kind of transmit it to the decoder. Then you don't actually need this RSS step at all. But this is kind of a relaxed notion of error correction. It's like a private error correcting code where it's an error correcting code with like a private classical sidechain, which I guess for practical purposes, like an error correction is probably often enough.
It's probably strong enough.
Yeah.
And but it doesn't simplify the rest of the construction.
Yeah, it doesn't simplify it just means we don't need the robust secret sharing.
This is because you're considering adversarial noise, right?
If you share a key, the same bounds hold?
Yeah, so the key, as we'll see, the key will basically introduce like an additional epsilon loss in parameters.
No, I mean like the lower bound that you had at the beginning. Like,
Oh, yeah.
the over 4, like, okay.
Yeah, these singleton bounds are, so classically, I think a secret key will let you. So classically, it's a different story.
Okay, but phantomly it's the
Yeah, quantumly,
one of my shared over 4.
yeah. Or, oh, you mean for exact?
Yeah.
I'm not sure. I think, because usually with the secret key, we think of it, it's like a random draw, so there's usually going to be some chance of a failure. Maybe, but, I mean, I guess you could always like do teleportation. Oh no, but that requires.
Okay,
Yeah, I'm not sure.
Is the answer no?
Yeah, I'm not sure about exact correction with the secret key, but that's an interesting question. So this is just a restatement of our main result. In a second, I'll show how we put everything together, and we get this family of efficient quantum error correcting codes with any rate R, constant alphabet size for a fixed small constant gamma, that correct up to roughly the singleton bound, the quantum singleton bound, with an exponentially small recovery error. So our encoding algorithm is shown here. Basically, we start with a message fee. We first draw a random classical secret key kappa, and we run the PTC encoder to get a slightly longer message here. Then we encode this in the quantum list decodable code to get like our quantum list decodable code word here. And finally, finally what we do is we take the secret key kappa, we encode it in the RSS scheme to get kind of this green code word, and we just kind of append the robust secret sharing symbols to the quantum list decodable code symbols. So you kind of glue these symbols together. The key point being that this PTC we'll use is very randomness efficient. So even after encoding in the robust secret sharing scheme, the size of this code word is still relatively small compared to the size of these symbols are still much smaller than the size of these list decodable symbols. So this additional appending step doesn't really impact the rate. So now to decode, we assume that there's some corruption. So some of these blocks are red. They've been corrupted by the adversary. The first step is just to separate out the robust secret sharing encoding from the quantum list decodable part. We apply the RSS recovery to recover the secret key kappa with high probability. And we separately list decode our list decodable code to get some state here, along with a list of possible errors, with the guarantee that one of these errors is the true error that occurred on this state. So now we kind of take our secret key kappa we've pulled out, and we use it to run the PTC decoder, which takes as input this state in the list and outputs a message. And this is our decoded state, which will hopefully be equal to the original message feed. So I guess the first two steps are I've already explained. So I guess the main thing left is kind of what exactly is going on here. So I've kind of hinted at this algorithm, but really what we're doing with the PTC decoding step is just kind of loop through the list of errors, find some error, some EI in the list such that when we apply EI dagger to our state psi, the PTC detects no error. And then we assume that's the true error and we invert it. Now, in general, the PTC, by its property, like by the definition of a PTC, it will, with high probability, detect all the extraneous errors in the list just by a union bound. But the one key point is that this guarantee only holds if the list is independent of the choice of secret key kappa. And the robust secret sharing scheme has already hidden the key from the adversary so that the decoder can recover it. But if you look carefully, the secret key is also kind of implicitly incorporated into the quantum list decodable code. Because we first encoded our message into the PTC. So the PTC code word inherently has some information about kappa. And we're then encoding this into the list decodable code. So maybe the adversary could somehow kind of look at the quantum list decodable code word and learn something about kappa. But it turns out that this actually can't happen by this property called local indistinguishability, which at a high level says that all good distance quantum codes are actually robust secret sharing schemes. So if you look at any local part of a good quantum code, you can't learn anything about the message. And this actually helps us to hide the secret key kappa from the adversary. And combined with the RSS property, this actually shows that the adversary can't learn anything about kappa. Of course, this is just high level. You need to kind of do this out formally, but that's really the intuition.
So Luis, is this latter part also where there is a departure in the quantum word from classical?
Yeah, exactly. Right, so if we had a classical list decodable code near the classical singleton bound, there's no way we could have this hiding property. Whereas quantumly, we actually have to have this hiding property.
Just you're saying that the pressure cannot learn kappa.
Yeah, just to clarify, like the adversary they see both parts, and the fact they can't learn kappa from the green part is by definition. The more subtle thing is that they can't learn anything about kappa from the blue part.
Did the adversary just decode everything, learn kappa, encode back, and then corrupt things?
Right, I guess so they're only allowed to access at most 1 minus r over 2 fraction of the symbols by assumption.
Oh, access and not corrupt. I thought they could corrupt. Okay, sure. I thought they could access all of them, but just corrupt a few of them.
Right. Oh, I see. So this is interesting. It's a slight departure from the classical model. The reason, so yeah, we do assume they can only even access delta fraction. I think the reason we do that is because quantumly, it doesn't really make sense to access something but not corrupt it. Because if you...
Well, you could use everything, learn kappa, encode back, and then corrupt a few of them, right?
But how are you going to observe? I guess if you learn anything about, if you perform any measurement, you could corrupt.
Kappa is classical, right?
Oh, so you're saying you could somehow decode?
Decode just the first part, learn kappa, encode it back, and then corrupt.
I think the model says that you're not allowed to do that, right?
Yeah,
That's
that was my
but it is a nice question, right? Like if you say, well, actually, this is like a quantum code with a classical code like written down next to it, right? Like maybe I should allow the adversary to see the whole classical part.
Yeah, I guess.
Yeah.
Right. I guess the thing here is we've incorporated the classical part into the quantum part, but I guess what you're saying is we could, in theory, say we allow an adversary to do any operation whose output only modifies delta fraction. Yeah. I think in this case, yeah, this would probably break. Okay. I haven't thought about that model before. But that's very interesting. Yeah, I guess maybe one thing on that model is that typically, like, if the adversary can already access everything and their goal is just to corrupt, they would just corrupt it, but maybe not. Maybe there's applications. Right, so I guess that's kind of how our construction goes. I guess I'll now describe this follow-up work by Thiago, who actually got this more powerful technique for filtering the list with a new cryptographic primitive. So the motivation is that we often care about binary alphabets, and we could ask, like, do our techniques extend to binary alphabets? And the answer is no, because when we append these RSS shares, we necessarily increase the alphabet size. So even if the quantum list decodable code had a binary alphabet, so all these blue symbols were a single qubit, then we still need to append something to transmit the secret key. So we need to increase the alphabet size by at least 1. So there's just kind of no way with this approach to get truly like binary alphabets. So this raised the question, like, what if we could replace our PTC with some keyless authentication? Maybe that would mean we don't even need this robust secret sharing in the first place. And this is exactly what these Pauli manipulation detection codes do. So they're a unitary encoding that permits the detection of every possible Pauli error with high probability. So intuitively, what it means is that we take some quantum state, some message, we apply an encoding, and now the point is for any possible Pauli error, this will take our code state to something that's almost orthogonal to the code space. And formally, it just means, yeah, any code state for any non-identity Pauli, applying this non-identity Pauli to the code state gives something whose projection onto the code space is at most epsilon. And here you can think of epsilon as like 2 to the minus order n. And in general, like this detection algorithm is just kind of measure with respect to the projector onto the code space. So this follow-up work of Thiago has a few implications. It gives an alternative construction of our result that avoids the need for robust secret sharing. It allows you to look at the binary alphabets where we can't quite get the same result because we don't know like efficient, optimal list decodable codes. against adversarial errors. But actually, for erasures, so where we know the error locations, then random codes actually work because you can always efficiently list decode from erasures. So one implication is that using these PMD codes, you get approximate error correcting codes near the singleton bound for known error locations over binary alphabets. And there's also implications for keyless authentication on qubit-wise channels. So I guess I'll just kind of wrap up by briefly describing this, kind of how these PMD codes fit into our construction. The encoding is almost the same, except we replace the PTC with a PMD. So we first encode in the PMD, and then the quantum list decodable code. And to decode, we again list decode from the QLD. We do our list decoding. Then instead of a PTC decoding, we do a PMD decoding. And just to add a couple more notes on that. So this decoding algorithm is basically the same as we had for the PTC case before. The main difference being, so now this is kind of inherently quantum. We need to literally loop through all of these errors. We need to try applying the inverse, perform a measurement. If it detects an error, we invert, we unapply this inverse error and move on to the next one. If there's no error detected, we assume it's the true error and return the resulting state. I guess the key point here is this is now an inherently quantum decoding algorithm. We're literally performing a measurement for each of these list elements. And we really do need to argue that kind of each of these measurements won't perturb our state psi too much. So we need some sort of like gentle measurement argument to show that. But it all basically works out because all of these detections happen with such high probability that they really can't perturb the state very much. And I guess finally, we also need to construct PMD codes, which in the same follow-up work I mentioned, they achieved with basically just taking an appropriate PTC and encoding our message state as a uniform superposition of PTC encodings over all possible secret keys. It turns out that for certain PTCs, this gives a PMD. So I'll just conclude with some open questions. The first one is, can we get efficient binary approximate quantum codes approaching the GV bound? I guess what I didn't mention is that the singleton bound is, we really only know how to achieve it for large constant alphabets. For binary alphabets, kind of we really think we can only hope for this GV bound, which is a weaker bound. And if we had, for instance, like list decodable, really good binary list decodable codes that are efficient, we could get this. But we don't even know those classically. So maybe some really, really big breakthrough in list decoding could get this. But it's unclear as of now. And I guess two other points. One is it's not clear how to list decode non-stabilizer codes. We have only actually defined list decoding for stabilizer codes, but classically you can list decode nonlinear codes. So it is a little weird that there's this discrepancy. And finally, it would be interesting if we had more applications of quantum list decoding. I guess classical list decoding has a number of applications in complexity theory, whereas quantumly so far, we don't really know kind of analogous results. So thank you.
So do we have further?
I think somehow I missed the intuition for why this doesn't work classically, where you can't reduce this to approximately classically. What's the...
Right. I guess in our approach, the thing that breaks down is the robust secret sharing scheme.
There are classical secret sharing schemes.
Yeah. So we actually use a classical secret sharing scheme. The thing is, those only correct up to 1 minus r over 2. Like those are only robust up to up to adversaries of weight 1 minus r, which is quantumly you need, classically you would need 1 minus r, which is not possible.
Oh, I see. So it's not really that you can't do it classically. It's just that everything goes through, and you just get up to the same 1 minus r over 2. It's just that the classical thinking about.
Yep. Yeah. The goalposts have shifted.
So, got it. Thanks.
Sorry about that. I'm not familiar. Sorry, yeah, I'm not sure. Maybe we can talk about that more.
Why is the GB bound like the next goalpost? Like it's a different kind of bound, right? It's an existence, lower bound. Why is that the next?
Right. I think it's because we don't know if we can really get much beyond the GB bound, but I think with random list decodable codes, we could at least hit the GB bound, so we know inefficiently we can achieve it. So
even for quantum?
Yeah. Okay. So yeah, it's really a de-randomization / like algorithms question.
Yeah, just so is it you've been using approximate quantum error correction to get better results, but if you don't want to get better parameters, but you just want to simplify existing constructions using by allowing approximation, is this known? Are there examples for that?
I'm not sure, but that's an interesting question. Yeah, maybe there's even some like practical benefit of relaxing to approximate. I'm not sure.
Okay, so perhaps we can thank Lewis again. And just to remind you that